Okay, we're going to go over the Chapter 5 RAEs that I assigned you guys. The first one I assigned, or if we're going to start at the beginning, we have question number 1. It says, what characteristic property of two liquids must differ if a mixture of them is to be separated by fractional distillation? So the characteristic property is boiling point. So two liquids must have different boiling points in order for us to be able to separate them by fractional distillation. So the answer is boiling point for number 1. Okay, number 3 says, the temperature time graph shown in figure A was made during the fractional distillation of a mixture of two liquids, E and F. Fractions were collected during the time intervals 1, 2, 3, and 4. Liquid E has a higher boiling point than liquid F. What liquid or liquids were collected during each of the time intervals? I'm going to start with interval number 4. It says that liquid E has a higher boiling point than liquid F. So if liquid E has a higher boiling point, that's the one that's collected during time interval 4. So the other liquid we know has to be collected during time interval 2 because it's the only other place where there's a plateau. And remember, the plateau tells us that this is where a substance is boiling and changing from one state to the next. And because boiling point is a characteristic property, we know that it's going to be unique to a specific substance. So if we have two substances or two different liquids, and we know that liquid E is the one with a higher boiling point, we look for the plateau at a higher temperature, so that's E. And then liquid F then has to be the other boiling point, the lower boiling point on the graph. So this one is liquid F. Now, as we talked about yesterday when I showed you guys how fractional distillation works, we know that from time interval 3, during this time interval right here, a little bit of this substance right here, during this part here, is collected, and then a little bit of this substance here gets collected during time interval 3. So time interval 3 is collecting a little bit of substance E, right here at the beginning, right where it starts to boil, and a little bit of substance F right at the end here where it's finishing boiling off. So time interval 3 contains both liquids. Time interval 1, most likely there's not very much liquid that's collected during this time interval because we're starting probably around room temperature, and as the temperature goes up, nothing's boiling yet, so there's nothing evaporating and boiling off until we get to right around here. So there's a chance that we might collect a little bit of liquid F right here, right before we move the delivery tube from the first test tube to the second one. So right here, right where liquid F starts to boil, is where we might collect a little bit of that liquid. So time interval 1, we probably collect just a small amount of liquid F. Time interval 2 is all liquid F. Time interval 3 is a little bit of F and a little bit of E. And then time interval 4 is all E. The next one is number 6A. Okay. In table 5.1, which substances would be liquid at room temperature, 20 degrees? Which would be solids and which would be gases? Okay, so we saw a question like this back in chapter 4, and you're going to see a question just like this on the chapter 5 test, which means that it's very likely there could be a question like this on your semester exam. So let's take a look. So I'm going to write something down on a piece of paper, so I'm going to have to turn the page to look at the table. So I'm looking for, at 20 degrees, which ones are solids, which ones are liquids, and which ones are gases at that temperature. All right, so let's go back to table 5.1. Okay, 5.1, here's the table. You can see I've already, this morning when I went over it with first period, I wrote in my book a little bit. So based on this information, obviously we're not looking at density or fuel gas or common products of this or kerosene. We're looking at the freezing point and boiling point. That's going to help us figure out which state of matter each one is at 20 degrees. Okay, so before you start trying to figure this out, I always have to kind of start with what I already know. So before I look at all the numbers, here's what I'm going to do. I know, let's see, when a substance, let's see, what's the best way to do this? When a substance freezes, yeah, okay, we'll do it this way. When a substance freezes, I'm going to just start with what I know. So freezing point. When a substance freezes, it starts off as a liquid and it turns into a solid. Okay. When that happens, the temperature is going to decrease. Okay, this is freezing point. When a substance boils, it goes from a liquid to a gas. And when it boils, this is boiling point, the temperature is going up. Okay, so this is what I know about freezing point and boiling point. The other thing I know is that freezing point is the same temperature as the melting point for a given substance. It's just a matter of the direction that the temperature is going. Just because they both occur at the same temperature does not mean they occur at the same time. And we've had this conversation before. So melting is just when the temperature is going up, and freezing is when it's going down. Okay, so if I set this up like a continuum, like a number line with temperatures. Okay, so let's think of like really low temperatures over here and really high temperatures over here. The progression is going to be from solid to liquid to gas. So as the temperature increases, a substance can go from a solid to a liquid. As it continues to increase, it can go from a liquid to a gas. When it goes from a solid to a liquid, that's its melting point, which is the same thing as its freezing point. And when it goes from a liquid to a gas, that's its boiling point. Okay, so I'm kind of just getting straight in my head what all of these numbers mean. So here's kind of like our continuum. It's kind of like, think of this as a number line. If this was the number line for water, we would show 0 would be here and 100 would be here. Okay, we're not going to put numbers on it because every substance has a different freezing and melting point compared to its boiling point. But this just kind of sets up the foundation so we can then kind of analyze the data table here. Okay, so I'm going to do this. I'm going to fold this in half. So we're looking at 20 degrees. So basically we're going to go through all of these and figure out what state of matter will each of these substances be at 20 degrees. Alrighty, so here's my freezing point and then my boiling point. Here's my boiling point there. So there's our timeline. Alright, so let's look at methane. Methane will freeze at -182. Okay, so anything below the freezing point, it's going to be a solid. Anything above that freezing point, it's going to be a liquid until it gets to its boiling point. If it's above the boiling point, if it's above 161, it's going to turn into a gas. Okay, so 20 degrees Celsius is definitely well above the boiling point. So methane is going to be a gas at room temperature because 20 degrees is well above the boiling point. And if it's above the boiling point, it's going to be a gas. So methane is a gas at 20 degrees. Ethane is also a gas at 20 degrees for the same reason, because 20 degrees Celsius falls well above the boiling point. Same thing with propane, and same thing with butane. So these first four, all of them have boiling points well below 20 degrees, which means 20 degrees falls above their boiling point, and if it's above the boiling point, it's going to be a gas. Now, just to kind of simplify this, the rest of them, and you can look at this as you go through it, every single one of these 20 degrees will fall in between the freezing and the boiling point for all of these substances from pentane all the way down to hexadecane. So because 20 degrees falls in between, where am I going? In between the freezing point, right here. This is the one I'm looking at. Okay, so in between the freezing point and the boiling point. So 20 degrees falls in between these two. If you're in between the freezing and boiling point, it's going to be a liquid. And all of the rest of these fall in the same situation. All of them have 20 degrees that falls right in between the freezing and boiling points. So all of these are liquids at 20 degrees. None of them are solids at 20 degrees. Because for them to be solids at 20 degrees, their boiling point would have, their freezing point would have to be above 20. And none of them have a freezing point above 20. So that's how you answer 6A. That's one that you will definitely see again on the Chapter 5 test. And quite possibly you could see on the semester exam. So you might want to listen to that a few times if the rationale doesn't make sense to you. All right, let's look at number 8. Okay, 8 and 9. So number 8 says, sawdust and sand can be separated by flotation in water. Could sawdust from two different woods that had densities of 0.6 and 0.9 be separated by flotation in water? And then, what about flotation in decane? All right, so let me grab another sheet of paper. So, for separation by flotation, the point that you have to remember here is that, let's say we have a beaker of water. The density of water is 1. In order to separate two things by flotation in water, one of them has to have a density less than 1, and one has to have a density greater than 1. The one that's, if one has a density less than 1, it's going to float. The other one would have a density greater than 1, it would sink. Now, the two solids that they're talking about in this question here have densities of 0.6 and 0.9. Both of those are less than 1, which means both of those would float. So in this case, separation by flotation will not work, because for separation by flotation to work, one has to float and one has to sink. And both of those are going to float. So this will not work with water. So let's look at decane, decane is the one. So let's go back to table 5.1. I'll do that really quick. 0.730. 0.730. Okay, so this is the density of decane. And this one's going to work just fine, because the one whose density is 0.6 is going to float, and the one with a density of 0.9 will sink, because it's more dense than the liquid, and this one is less dense than the liquid. And so that this liquid would be able to separate these two solids by flotation. Number 9. The example in section 5.3 of separating sand and sawdust requires that the substances have different densities. What needs to be true about their solubilities for this process to work? Okay, so in order for separation by flotation to work, the first thing is they have to have different densities, one greater than the liquid, one less than the liquid. In terms of their solubilities, both substances need to be insoluble in whatever liquid it is that we're using to separate them. They have to be insoluble, because we want one to float and we want one to sink. And if one of them dissolves, then it's neither floating nor sinking, it's dissolved, and then this process won't work. And then we would have to use a different process. So both substances have to be insoluble in order for this process to work. Alrighty, question number 10. In what characteristic property must two solids differ if they are to be separated by the method used in this experiment? This experiment that they're talking about is 5.4. So, in this experiment, the characteristic property that we're using is solubility. We would need one substance to dissolve into the filtrate, and then one substance to not dissolve so that it can get stuck in the filter paper and separate out. So what you need to think about is the lab that I showed you guys, that demonstration with the salt and the sulfur. When we put this mixture of salt and sulfur into the test tube, the salt dissolved, the sulfur did not. So the sulfur, when we filtered it, got stuck in the filter paper, and then the salt went with the water through the filter paper. We call that the filtrate. And that's how we were able to separate them, based on the fact that one was insoluble and one was soluble. So the characteristic property that they're looking for in question number 10 is solubility. Question 13. Suppose two substances have the same solubility in water at all temperatures. Can they be separated by fractional crystallization? Why or why not? No, they absolutely would not be able to be separated by fractional crystallization. In order for fractional crystallization to work, one of the substances needs to be more soluble at a certain temperature than the other one. So that basically, if you think about the process that we went through looking at 5.5, when we heated up the mixture, one of the substances dissolved and the other one did not, which then allowed us to filter the substance and then cool cool down the filtrate and have the precipitate come back out again. So if they had the exact same solubility at all temperatures, that means as you increase the temperature, both substances would dissolve equally, which would not allow us to be able to separate them by filtration at that point. So fractional crystallization will not work if two substances have the same solubility at all temperatures. And then 18 and 19. To what temperature should a mixture of nitrogen and oxygen be cooled in order to separate them using fractional crystallization? So if we have a mixture of nitrogen and oxygen, if you look back to section 5.7, the first step in the process is to liquefy those two gases. In order to liquefy the two gases, we have to cool them down to the point where they will condense, which is this point right here. So we have to cool down this mixture of nitrogen and oxygen to at least negative 196 Celsius in order for that mixture of gases to turn into a liquid. So at least negative 196 Celsius or more than that is the temperature that we need to cool it down to in order to then fractionally distill it. And then 19. Could nitrogen, oxygen, and hydrogen occur together in a mixture of liquids? The answer is no, they cannot. Because in order to get hydrogen to the point where it's a liquid, we have to cool it down to negative 253, or, well, between negative 253 and 259, somewhere in here is where hydrogen will be a liquid. However, if we were to cool down a mixture of all three of these to negative 253, these two would then be solids because it's below the melting point, which is the same as the freezing point. So these two at negative 253, which would be on this side, in terms of solids, liquids, and gases, these two would be solids at this temperature. And this one would be a liquid. And then in order for these two to be liquids, it has to be, between these two temperatures, but that's not cold enough for this one to be a liquid. So when these two are liquids, this one's a gas. So there's no way for us to get all three of them to be a mixture of liquids at the same time. And those are the RAEs that I assigned for Chapter 5. If you have any additional questions, please let me know.